Okay, so it's my turn. Let me thank the organizers for this kind invitation. I'm really proud and happy to make this introductory talk on the nuclear physics point of view of nuclear astrophysics. Okay, so this is just a short outline of my talk. I will discuss the nuclear physics aspects in the abundance curve, then I will move to the features of thermonuclear reactions. Then I will discuss some of the experimental approach that will be probably topics of the next SNAQs, and then I will focus on some physics cases if I have time. Okay, let's consider that the first half of the last century was really crucial for this kind of interdisciplinary branch that we call nuclear astrophysics. And indeed, somehow the famous seminal B2FH review paper that was published in 1957 can be really considered the basis of the modern nuclear astrophysics. Indeed, the authors clearly stated the nuclear reactions are responsible for both energy production and the creation of the elements, and they already somehow summarize all the work that was done before, and they highlight 4 environments for nucleosynthesis that we have already seen during our previous talks: the cosmological nucleosynthesis, namely the creation in the Big Bang, the stellar nucleosynthesis, the explosive one, and the galactic one. So in order to highlight our current belief in terms of nucleosynthetic source of the elements in the solar system, I may just use this nice periodic table where each element is color-coded by the relative contribution of the nucleosynthesis source. And you can, of course, you see something that was already stressed in the first 2 talks, and in particular that hydrogen, helium, and lithium the Big Bang have been synthesized during the Big Bang. And of course, hydrogen and helium mostly, and just a tiny part of lithium. And this is also why in astronomy a metal is any element other than hydrogen or helium, and which are indeed the primordial nuclei, and the metallicity is an indication of stellar activity after the Big Bang. However, if I go to the abundance curve, it appears that a lot of nuclear physics is indeed there. In particular, so the first question is why the Big Bang nucleosynthesis didn't go beyond lithium. And this is essentially because of the lack of stable nuclei with mass number 5 or 8, and also because of the rapid decrease in temperature and density that didn't allow for the nucleosynthesis to go on. And the next elements after hydrogen and helium are lithium, beryllium, and boron, which are very poorly abundant, essentially because they are not produced in stars. And starting from carbon, we have seen that the nucleosynthesis takes place in stars. And we realize already that we have a kind of staggering in the abundance that was deeply studied during the first 10 years of the last century, and now it became a rule that is called Oddo-Arkins. Indeed, what we observe is that from carbon, elements are produced by buildup from alpha particles, and we have an alternatingly larger abundance of even nuclei with respect to the odd ones. And this is essentially connected with the pairing in the nuclei, which makes nuclei more stable. Another thing that I want to highlight is that we have peaks in correspondence of the so-called alpha nuclei. In particular, we have peaks for the oxygen, so we have peaks for all these alpha nuclei, but in particular for what we call magic number nuclei. Some combination of value of Z and N, we have a larger abundance, and this happens quite clearly for oxygen, for calcium, for iron, and not very clearly after iron. Indeed, something happens after iron, and we have already learned a lot from Jordi talk, because iron corresponds to the larger binding energy for the nucleus. So all the reactions which take place in stars up to iron produce energy, and so they are very favorable for the star, because otherwise the star cannot survive the gravitational collapse. And after that, after iron, essentially what is produced after that is useless in terms of energetic gain for the star. And so somehow even the, let's say, the nuclear physics rules, they somehow change, and I should say that they are also quite unknown for the moment. Another feature that I would like to draw, to highlight, is that from carbon up to iron, we experience a kind of exponential decrease in the abundance, while starting from elements beyond iron, we have a much smoother dependence decrease while Z is increasing. This is essentially, we will come back later on this aspect. This is essentially due also to the fact that the nuclear processes that are governing the nucleosynthesis are changing. Okay, so let's start highlighting some nuclear physics features, in particular what nuclear physics can provide to modelers are basically these two numbers, so the total reaction rate and the energy production rate that is strongly connected to the total reaction rate. And the nuclear physics information inside the total reaction rate is this product, which is here in brackets, which is the combination of the velocity distribution of nuclei inside the plasma and the nuclear cross-section. What it is usually done in terms of velocity distribution is assuming to have a plasma in thermal equilibrium at temperature T, and non-degenerate one and a non-relativistic one. So we can somehow parameterize this velocity distribution in terms of a Maxwell-Boltzmann one. As for the cross-section, we cannot use a nuclear theory a priori to determine it, because it is very strongly depending on the properties of the nuclei and also on the reaction mechanism. Just to consider that you may have, so shortly speaking, a non-resonant process or a resonant process, and this would change completely the story. So how we can manage? So we have to make a joint venture between experiments and the theory in order to get back to this stellar reaction rate. And so if I come back to the abundance curve, as I highlighted, we have this exponential decrease up to the iron peak, and then we have something much smoother. Indeed, this first part of the abundance curve is strongly dominated by nuclear reactions between between charged particles. And if you just think the temperature, typical temperature in quiescent burning, just let's consider our sun, which has a temperature of 15 million Kelvin. The thermal motion provides an energy which is of the order of few keV. So it's really a small amount of energy, and we are deeply dominated by the Coulomb barrier. And essentially the only way for a reaction to take place is through the quantum tunneling effect. And the tunneling means that our probability for a reaction to occur in such a condition is completely dominated by the tunneling probability. And that at a low energy, this tunneling probability is parameterized, is provided by this exponential factor, which is called the gamma factor. So essentially what we have inside this sigma b, that is the relative probability, is the convolution of two behaviors that are given by the high energy tail of the Maxwell-Boltzmann distribution and the behavior of this gamma factor. And the convolution of these two behaviors provides what is called the gamma peak. The gamma peak represents the most effective energy region for thermonuclear reactions to take place, and it is also a guide to tell us where the measurements should be carried out. However, the problem is that this E0, the so-called gamma energy, is something that of course depends on the reaction and on temperature. But if you just have a look at this table, you see that if we consider just 3 of the possible reactions taking place in stars, we see that this gamma energy is always very, very low and much lower than the Coulomb barrier. And this, of course, means that we are faced with a decrease of the cross-section, a huge decrease of the cross-section that is can be even of the order of picobarn. And this means a very challenging adventure for the experimentalists. So a strong sensitivity to the Coulomb barrier. And this is also the reason why the burning in the star takes place through separate stages. So we have hydrogen burning, helium burning, carbon, oxygen burning. Somehow these complete the answer to a question that was asked to George in the first talk, after the first talk. So if we look instead to the second, I would say the second half of the abundance curve, so after beyond iron, this region is dominated by neutron captures because conditions are changed. So the iron, we say the iron has the highest binding energy. The star doesn't gain anything in terms of energetics. So basically all the reactions involving charged particles are somehow inhibited. So the easiest way, the most convenient way to proceed with the nucleosynthesis is through neutron captures. Neutron captures have the advantage indeed not to have the Coulomb barrier, and typically, so since the neutrons are quickly thermalized and we have these kind of energies, we have cross sections which are not very very small, and typically the cross section has this kind of 1/v behavior. That means that when you consider the product between sigma and b, you get a constant slope, which accounts for the almost flat abundance distribution that we see in the abundance curve. Okay, so maybe I can just try to make a list of the of the features we have seen up to now. In particular, if we just separate between quiescent burning and explosive burning, we may say that the quiescent burning is is governed by this range of temperature from million to 100 million Kelvin. We have energies that can range from few tens of keV to some MeV for heavier systems, but we are anyway below the Coulomb barrier, so the cross section can really be very, very small. The average interaction time is of the order of 10 to the 9 years, and the unstable species do not play a significant role. So since we have this low cross-section, the main issue for for reactions that are involved in the quiescent burning are their very poor signal to noise ratio. So how we can face, how we can try to handle with this issue. So we either do the extrapolation procedure, as I will show in a minute, or we can try to run for longer periods, so to perform longer measurements, or to use ultra pure targets to have high beam intensities, high detection efficiencies, and other kind of requirements. I can continue. For the explosive burning stage, what we have is, of course, a larger temperature, which is larger than, let's say, 10 to the 8 Kelvin. The energies are already of the order of MeVs, so we are approaching the Coulomb barrier, and this means let's say a more comfortable cross-section, and these somehow can avoid the extrapolation procedure. We have average interaction times of the order of seconds, and the unstable species do play a significant role. What are the main issues for the explosive burning stage? So that we are handling nuclei that in most of the cases they have unknown nuclear properties. And we cannot rely on what we know from the stable nuclei. That's another problem. And the other issues is that the beam intensities of radioactive beams are several order of magnitude lower than the stable beams. So just to list a number of requirements, of course, we have to provide radioactive beams. We need to run experiments with large area detectors, high detection efficiency, and in this case, I'm just mentioning here the storage rings that we will see later. So if I just want to make a focus on the need to use the extrapolation, we may say that what it is usually done is to measure the cross-section over as wide a range as possible, and then to extrapolate it down to the gamma peak. Of course, the extrapolation, I mean, can be dangerous, and first of all, the nuclear physicists have introduced something which is more comfortable to be extrapolated, and that we call S factor. So the S factor, indeed, you can see is constructed starting from the cross-section by multiplying for this exponential factor, which is the inverse of the gamma factor, and is introduced to remove the bulk of the Coulomb suppression. But however, even if we are extrapolating something which is a much smoother function of the energy than the cross-section, we are entering, let's say, some unknown region where there might be unknown resonances or wings coming from subthreshold resonances. So somehow the extrapolation is something that people want to avoid. And how to avoid extrapolation? We may try to approach some alternative solutions. For example, people have tried to run experiments in underground facilities in order to reduce the cosmic background. We have several examples. We have the Luna experiment in one of the 4 national laboratories in Italy. We have the Felsenkeller laboratory in Germany, we have Casper in the USA, and we have Juna in China. And indeed, the underground facility can be particularly suited to perform gamma spectroscopy. We can also run surface experiments using passive shields, or running in inverse kinematics, doing non-inclusive experiments, but trying to run in coincidence mode if the signal to noise ratio is not too low. And we can also make use of particular instruments like the recoil separator that here I'm just showing a draft of the ERNA recoil separator that allows to separate the reaction products from the unreacted beam and disperse these products according to the mass to charge state ratio. Otherwise, we have another nice experience at GSI using storage rings. This is something very important, in particular when we deal with radioactive beams, because this is a way to overcome the beam intensity limitations. Indeed, the idea is to make the beam recirculating many times, and in such a way the beam has several chances to interact with the target. Otherwise, we can also apply indirect methods in order to tackle the nuclear physics reactions. Okay, so I want to just to make an highlight on the background, on what we gain going underground. In particular, so the main sources of background are those due to natural radioactivity, so from uranium and thorium chains and from radon. We can have also, of course, we have cosmic rays, and we can have also another source coming from quite energetic neutrons that are produced from the interaction of cosmic rays with the shields. If you have a look at a typical gamma spectrum on a surface laboratory, we have a contribution below 3 MeV in terms of gamma energy that is provided by the natural radioactivity, while above 3 MeV we have this contribution from cosmic rays and neutron induced. So if we go underground, what happens is that we are you see, we are completely free from this background about 3 MeV, while we still keep something that comes from the natural radioactivity. Of course, this depends on the location where the underground laboratory is built. Of course, we can say that having this part of the spectrum free from background is already quite good advantage for capture reactions having high Q value. So the underground facility is very suited when we have to run experiments with gamma spectroscopy, where gamma spectroscopy plays a role. Of course, it cannot be so crucial when reactions, when charged particles, products are involved. I want to show you an important result that has been obtained by the LUNA collaboration during their first part of activity during this period, so from 92 to 2001, with a small accelerator. Just to highlight, to show that how difficult can be to run an experiment. So in 9 years, this collaboration could run just a couple of crucial experiments having to do with this kind of counts per month. So the 1 count per month on the left side, 50 counts per day, so a bit better in the second experiment. And so they had to run for a really long time. And in particular, this result from the left-hand side, that it's an important reaction in the solar PP chain, was kind of breaking through result. The experiment indeed was performed in order to test the presence of low-lying resonance, a resonance in the gamma peak that was predicted in order to solve the reduction of the neutrino, the solar neutrino flux. And however, the resonance was not found. There is no resonance in this low energy part of the spectrum, and we know that the problem of the solar neutrino reduction was then solved with the neutrino oscillations. And thanks to this experiment, we also learned an important point of the nuclear reactions in the extremely low regime. And indeed, this increase in the cross-section can be an intrinsic limitation of the experiments at very low energies. Indeed, this increase in the cross-section is due to the electron screening, so to the electrons that surround the interacting ions, and somehow they screen the repulsion of the two nuclei, and they provide this kind of, I would say, artificial increase of the cross-section that somehow we want to avoid, in the sense that to determine the reaction rate in a correct way, we need the bare nucleus factor. And this is essentially due to the fact that the screening due to the free electrons in a plasma is different from the one coming from the laboratory. So in order to assess the reaction rate correctly, we need, in any case, to come back to this, to the bare nucleus information. So how to handle this problem? Either we have a theoretical approach to remove the screening from the S factor we measure in the laboratory, or otherwise we cannot avoid the extrapolation. And from the theoretical point of view, people did a lot of experimental studies in order to better understand the screening, but in all experiments that have been performed so far, what happens is that the cross-section at low energy is larger than it can be accounted for by the upper limit provided by atomic physics models. This means that somehow screening is something which is not fully understood yet. Maybe it is not only screening, maybe there might be some complication due to the dynamics of nuclear reactions in this ultra-low energy regime, which is not clear. Anyway, so the problem is that when we need to run experiments at ultra-low energies where the screening becomes important, we cannot avoid extrapolation in order to determine the bare nucleus S factor. And so how to handle this problem? People in the last 20 years have tried also to work developing indirect methods that they allow to measure cross-sections in this ultra-low energy regime without the problem of the very low signal-to-noise ratio. And also they allow an independent analysis of the screening potential, and they can be also very promising to measure reactions with radioactive ions and the neutrons, as I will mention later. So indirect methods mean usually very straightforward experiments without the problem of the Coulomb suppression and without electron screening. However, we have an important issue that I have to mention. The problem is that the entrance channel and the reaction products can be linked by several reaction mechanisms. And in order to select the proper one, we have to apply the reaction theory. And so this means that we have to be very careful in the data analysis. However, nowadays, since people are working with indirect methods for many years, they know how to handle these problems. I'm just mentioning very shortly 3 of the indirect methods that have been used so far. Of course, there will be dedicated talks also during this SNAQs meeting. In particular, I would like to highlight how the Coulomb dissociation works. The Coulomb dissociation, in particular, is a method that has been developed in order to determine the absolute S factor of a radiative capture reaction by studying the reversing photodisintegration process. So here, the B nucleus is the product of the capture reaction. So the idea is to start from B, which breaks up thanks to the virtual gammas emitted by a very high Z nucleus. So thanks to the Coulomb field of this high Z nucleus. And then through the detailed balance, one can come back to the S factor for the radiative capture. Of course, the advantages are the possibility to use stick targets and also the possibility to work with larger cross-section for the inverse reaction. The issues that should be considered for each experiment is the presence of nuclear breakup that can contribute, in particular if the E gamma is large, or there might be contributions of other multiples. And here it's just a very simple connection between the two-body cross-section we measure, so coming from the reversing process, and the two-body cross-section we want to determine, which is of interest for nuclear astrophysics. The experiment has been already applied to several reactions and is going to be applied very soon at GSI to the carbon-12 alpha gamma, which is a very important reaction for nuclear astrophysics. The ANC is another complementary technique applied mainly applied and developed indeed for radiative capture processes. But the idea is to tackle this reaction by measuring a peripheral transfer into a bound state of the nucleus, which is produced through the capture. And here the idea is that assuming that the low energy, so the capture process occurs far from the nuclear surface, the cross-section is known, the cross-section depends on this ANC square. ANC is a parameter that measures the amplitude of the tail of the overlap function between the two-body system of the capture reaction. Now, how we can get this ANC? The idea is to derive this ANC by measuring a peripheral transfer reaction so another reaction into a bound state of this B nucleus. And of course, to do that, we need to know the optical model potentials. Otherwise, we have to run additional experiments in order to set the things. This technique was applied already to several reactions. And I moved to the Trojan horse method very quickly. So the Trojan horse method is indeed another alternative solution that can be applied to rearrangement reactions. And the idea is to determine the two-body cross-section of interest by measuring an appropriate 2 to 3 body process in a peculiar phase space region where the quasi-free kinematics rules. You can see here that the idea is that either the projectile or the target, say this small a nucleus, can be clusterized in terms of X and S. And in this phase space region where the experiment is performed, basically capital A will interact only with X, leaving the other cluster as a spectator to the process. The 2 to 3 body process is performed at an energy above the Coulomb barrier, and this will allow to, you see these clusters, so the A nucleus that we call Trojan horse nucleus, to overcome the repulsion wall and to bring the cluster X already in the nuclear field of capital A. Of course, this cartoon is then translated to difficult theory, and essentially we use this polar diagram with 2 vertices in order to better describe the process. In these conditions, what will happen is that in the second vertex here that describes the two-body reaction of interest, will not have Coulomb suppression or electron screening. Again, we have to make use of theory in order to connect the reaction, the cross-section we measure, namely this 2 to 3 body cross-section, with the 2-body cross-section we are interested in. In this simple formula, you see that since we have this proportionality sign, we need direct data in order to make the normalization of our cross-section to the direct data in order to have the cross-section in absolute units. The method has been applied many times, and there will be, as I told you, there will be for sure other dedicated lectures in order to go more deeply in this methodology. Okay, so let's, do I have still time, right? I don't know how much time.
5 minutes left, yeah.
Okay, so I can just dedicate what is last to describe a few cases of study. In particular, I would like, maybe I can skip or just go very shortly in the cosmological lithium problem. Then I would like to make a focus on the helium and carbon burning, and move, if I have time, to the neutron sources in this process, and just to give you some hints how to measure the N-gamma processes, which are important for the R process nucleosynthesis. You have heard several times today, the Big Bang nucleosynthesis provided us with already with some elements, but could not go beyond lithium. However, the Big Bang nucleosynthesis model has still something which is not solved, and it is called the cosmological lithium problem. The problem is that once we play with the Big Bang nucleosynthesis model, using as inputs a number of nuclear reactions that are connected. So this is the network of reaction which enter in the Big Bang nucleosynthesis model, and we put a few other inputs, in particular the baryon to photon ratio and the neutron lifetime. We can get an information on the abundances of these primordial elements. And then we can check if these numbers are in agreement with the numbers coming from observations. And what happens is that somehow, so the agreement is there except for the lithium-7. And indeed, the lithium-7, so you see here in this diagram on the right side, these green areas come from observations, while these blue and red lines show the calculations, and you see that the disagreement can be a factor of 3 to 4. So people are struggling to understand why. There might be the possibility to improve the observations, so to improve also the knowledge of the cross sections of the network reactions, so to add the new physics, in particular from the nuclear physics point of view, people are thinking to include, to add reactions in the network, in particular those involving the destruction of beryllium-7, since beryllium-7 decays into lithium-7, and so if it is destroyed first, this of course will affect the production, so the abundance of lithium-7. But of course there might be other solutions which are outside the nuclear physics area. Here just these come from the couple of attempts that have been performed in the last years. Of course, we have to run more experiments in order to tackle the problem if the problem has a nuclear physics solution. I will skip it. I'll go just to say a few words on the Ilium burning. In particular, we have learned that Ilium burning is a crucial phase of nucleosynthesis for all stars, and it is governed by essentially these two reactions: the triple alpha process that produces carbon-12, going through very nice, this is a very nice story that nature, it's a kind of present from the nature, the so-called oil state in the carbon-12 that allows us to have the triple alpha process running to produce carbon-12. This rate is quite well known, and the second process is the carbon-12 alpha gamma oxygen 16, which is instead poorly known. What we know, so what we need indeed is to know the cross-section at center of mass energy around 300 keV. But as you can see from this spectrum, we are still far from reach 300 keV. So we can just use calculations, extrapolations, trying to get information from spectroscopy studies to gather knowledge of levels in oxygen 16 that can be that are of interest for this reaction. In particular, this is a region where we may have interference between resonances and non-resonant components, and so this makes a really very difficult story. However, we have also learned that the carbon over oxygen ratio is a very important parameter that we have to know in order to understand the stellar evolution, the late stellar evolution of massive stars and type 1a supernovae. Here, just a list of forthcoming attempts, so people will try to investigate, as already they did, the beta decay of nitrogen 16 into oxygen 16, and further the oxygen 16 alpha decays, and so it goes to populate the entrance channel our reaction. There are other attempts that will be done in the future, like using intense gamma beams in order to photodisintegrate, in order to disintegrate the oxygen-16. Or, as I mentioned, there is an attempt to tackle the reaction through the Coulomb dissociation. And people are also, since many years, trying to infer the carbon over oxygen ratio in other ways, so looking out of nuclear physics, and in particular by studying the white dwarf seismology. So if I have still time, just a few words on the carbon burning. The carbon burning is another crucial phase for the stars, in particular for the nucleosynthesis of massive, intermediate and massive stars. And it is also one of the nuclear physics parameters determining what we call a map. A map is a kind of a threshold in map deciding where if the carbon burning will take place in a quiescent way. And it seems that it can also be the trigger for superbursts and type 1a supernovae. The carbon burning takes place through the fusion, mainly through the fusion of two carbon nuclei, and the two main channels are the alpha and proton channels. I want just to show you here that since the astrophysical region of interest is somehow below 2 MeV, so the region is from 1 to 3 MeV, but for quiescent burning is around 1.5 MeV. I want to show you here how the cross-section drops. So we are even around 10 to the minus 20 bar, and that means that running direct experiments around 1.5 MeV will be extremely challenging. And there have been also several attempts to extrapolate the behavior of this factor starting from higher energy data. But as you can see here, just some of these attempts, they differ by several orders of magnitudes. A couple of years ago, we did an experiment with the Trojan horse method using nitrogen-14 in order to transfer carbon-12 in order to make the fusion of the two carbon, and this is what we have obtained. We have so we could populate all the region of astrophysical interest, and we found several resonances that dominated the astrophysical energy. After that, there were other experiments done, directly from the Stella collaboration and from the group of Notre Dame, and data reported here. Somehow within the experimental errors we have the agreement, but still our data somehow they raised a lot of discussion, and at some point we are working, people are trying to do their best in order to measure below 2 MeV, and at some point we should come to some consensus S factor. So maybe, do I have time? Maybe I can skip these.
Oh, yeah. So I would like to skip it. Yeah. So that we give the option to ask questions. So.
Okay, now I want just to finish with this slide that concerns the possibility to measure the N-gamma reactions in the laboratory. So the N-gamma, the neutron capture reactions are very important for the processes, but of course they involve very short-lived nuclei and neutrons. So how to handle a reaction with two unstable nuclei. So what people are doing now is try to prepare the proper beam with short-lived nucleus ions, and to use a deuterium as a virtual neutron source. So This can be done by applying what is called the surrogate reaction method, something that is quite well assessed, even if, of course, it has several issues that should be handled for each experiment. Or we can also apply the Trojan horse method. Another nice idea that comes from GSI is to produce a Newton target from a spallation source of protons on tungsten in such a way neutrons are evaporated and then they can be thermalized and they used as targets. This kind of target can be put in a storage ring, and so we can this can be a promising technique to measure N gamma directly. So this is just my last slide, and I want to thank you. Of course, this was just an introductory talk, and I hope that other discussion can be done during the next SNAQs. Thank you.
Yeah, so there are some questions. And the first one is, what is the biggest uncertainty in the cross-section measurements?
Oh, so that's a bit harder to say. It depends how you run experiments. So you have to handle many factors. You can have a lot of systematic uncertainty coming in. You can just let's say control somehow good the statistical error, trying to run for longer times, but this is also it's questionable. Yeah, you can have also uncertainty coming from theory. I mean, it's not easy to answer. Maybe we should consider a dedicated experiment just to analyze together what kind of uncertainties we can find
In one of the forthcoming SNAQs.
In the forthcoming, yeah.
Yeah. So the second question is there a microscopic understanding or modeling of the screening effect in the target materials that are used for cross-section measurements? As you said.
Yeah, I would say that we don't have a real microscopic understanding because so people are really doing a lot of work trying to see if the screening is changing depending on which material is in the target, if it is a metal, if it is an insulator. But really something is not clear because all the numbers coming from this experiment, I mean, in terms of screening potential, much larger than the upper limits provided by atomic physics models. So now maybe it's not only screening, maybe as I was just mentioning, we have something from the nuclear physics point of view which is not understood yet. But of course, this is something which doesn't have anything to do with nuclear astrophysics in the sense that what we know and what we need in order to determine the reaction rate, it's just the bare nucleus factor. So this is also why people are starting running experiments in plasmas. So why the laser physics is developing a lot.
Okay. There is another question that says, is the ANC applicable to capture reactions on heavy nuclei?
Yeah, I think so. It can be done. Why not? The condition is that we have to have a peripheral reaction anyway. So the binding energy, so the connection between the two body system in the capture should be low. So, and the same for the transfer. Maybe for the heavy nuclei is even easier because the Coulomb barrier will help in the sense that we are for sure below the Coulomb barrier in the entrance channel.
Okay, so provided the projectile is charged.
Yes, yes, sure.
If it is about neutrons, that can only apply in the cases where you have a centrifugal barrier, which is large.
Sure, sure.
Not S orbital.
Not S wave, sure. Not S wave, but larger ones.
There is another question that says, how much lithium-7 is produced in Big Bang nucleosynthesis from a tritium alpha gamma lithium-7 reaction?
I don't know. Anyway, this maybe this is one of the most important, even if the gamma is in. I don't know. We should. I don't know. I don't remember. Maybe if I have some seconds, I can try to get this information.
As far as I know, all lithium-7 is actually from beryllium-7.
No, it's not. So if you look at the production as a function of the baryon to photon ratio, there's a dip. So I mean, the majority is produced indirectly through the beryllium 7, but the reaction which is mentioned in the chat actually is maybe, I don't know, something like 10% order of magnitude actually. So it plays a role, but not the dominant one.
The Triton alpha channel.
Yes, yes.
I have a table that I can have a look on the table, but
it depends, of course, on the nuclear reaction rate and nuclear experiments, and this is actually a reaction which would be interesting to study. So I don't know who is asking the question. So if you're brave enough to study it, please do.
Okay.
Yeah, the problem is to have a Triton beam. Yeah.
Yeah, so it's a high school question. With the naked eye, if you're looking at the sun and then you're looking at the lava from the Etna, you would say they have the same temperature. Do we have nucleosynthesis in the Etna?
I don't know, maybe I don't think we have nucleosynthesis there, but we can try. So
Okay, okay. I mean,
we don't have exactly the same energy. Come on.
But when you have nucleosynthesis in the laboratory just beside the Mount Etna, right? So
yeah. Okay. So that's kind of telling you that maybe there are differences between what you see on the surface of a star and what is inside there. So, I mean, like they are 15 million Kelvin. Or
yeah,
30.
just a tiny difference in terms of temperature, sure.
And then the last one, he says, nice talk, Aurora.
Thanks a lot.